amp power couplers. So two types of coupler we'll discuss. One is 90-degree hybrid coupler, other is 180-degree hybrid coupler. Then we'll extend that to something called rat race coupler. So what we'll do is we'll look at the concepts of coupler. These are called, first we'll look at the 90-degree coupler, which is called quadrature coupler. So from trigonometry or basic geometry, you know what is quadrature. Quadrature comes from the word quadrant. Quadrant means 180 or 360 degree. We divide that into 4 quadrants. Each quadrant is of 90 degree. So 0 to 90 degree is one quadrant, 90 to 100 second, 90 to 180 second, 180 to 270 third, 270 to 360 fourth. So there are 4 quadrants. Similarly, if there is a difference of 90 degree, we call those signals, when there is a phase difference of 90 degree, and then the signals are said to be in phase quadrature. So therefore, we are going to consider a quadrature coupler or a 90-degree coupler. In a quadrature coupler, the input will be split into 2 signals at the output. Usually, these signals at the output, they will be of equal power, but if it is required, you can divide it in the required or desired ratio. But usually it will be equal division. So we'll consider equal division power. So they will be equally divided into 2 parts, but the outputs, the 2 parts, will have 90-degree phase difference among them. And the types of quadrature couplers, they include 2 types. One is called branch line coupler or quadrature hybrid coupler. Second is called Lange coupler and overlay coupler. So we are going to see not the Lange coupler, but we will consider the branch line coupler and overlay coupler. Those you will see to some extent. Below you can see the pictures, practical. If you take a photo of a coupler, these are the practical photo of a coupler. In the bottom, the right hand side photo shows you the circuit of the coupler, and when the circuit is packaged for sale, packaged for use, the packaged coupler is shown on the left hand side. Left hand figure shows you the packaged coupler. So these are, if you see a physical coupler, it will look like this. Now let us come to what is the what is meant by quadrature coupler, how it works. This quadrature coupler is a device which is a 4-port device. In port one of the ports will give the input. The output will be at 2 other ports. The 4th port will be always isolated. There will be nothing in the 4th port, or 4th port will be matched. So the quadrature coupler is a lossless 4-port device. If it is lossless, then you know any lossless device or a lossless device has a S matrix which is unitary. So the quadrature hybrid will always have a unitary S matrix. It will be 4 cross 4 S matrix because we have 4 ports here. All 4 ports are matched. These all the 4 ports will be matched. Then the next property is the device is reciprocal. So if the device is reciprocal, then by the property of S matrix will be symmetric. So the S matrix of this port of this coupler is unitary and symmetric. These 2 conditions are to be satisfied. Now since all devices, all ports are matched, there are 4 ports. So S11 is equal to S22 is equal to S33 is equal to S44 because of matching all these are equal to 0. So the diagonal of the S matrix is 0. Then it is then we said that port 2 and port 3 there the power is equally divided. If the power is equally divided or signal is equally divided between port 2 and port 3, then the signal power is half, which means signal is 1 by root 2. So let us take 1 by root 2 common, and then in the matrix power is half, and they are 90 degree out of phase. 90 degree out of phase is denoted by J, which is root over of -1. So port 2 and port 3 there we will put J. Then we have reciprocal device. So the device is reciprocal. So this 1 2 will be J, 2 1 will be J, 1 3 will be 1, 3 1 will be 1. So this is what we are going to do. This way the S matrix, we can see that what is the S matrix of a quadrature coupler. Now in this coupler, port 4 is isolated from port 1. If I give input at port 1, there will be no output, nothing, no signal will come out at port 4. Or if something leaks out, it will be negligible. Port 2 and port 3 are isolated from each other, and port 2 and port 3 are in phase quadrature. So these are the properties of a quadrature coupler. This quadrature coupler it is used as a power splitter. Mostly it will split the input power. Now you can see in this figure we are showing two signals. Either you can give the signal either the red or the blue one. So either in port 1, when I give the signal input at port 1, the signal is indicated by red one. So then at that time there is no signal at port 4. We are not giving any input at port 4. If I give a signal at port 4, then at that time at port 1 there is no input. So at port 4 we are indicating at blue by blue. At port 1 we are indicating it by the red arrow. Now when we give the red arrow at port 1, it will come out at port 2 and port 3. Between port 2 and port 3, the signal, those red arrows you can see at port 2 and port 3, those red arrows correspond to the red arrow at port 1. So port 1 input, port 2 and port 3 output, those will be 90 degree out of phase, which means phase at port 2 minus phase at port 3 is equal to 90 degree. If we give the signal at port 4, then it will come out at port 2 and port 3, but it will be changed. The phase will change. Phase at port 2 minus phase at port 3 will be minus 90 degree. This must change. So minus 90 degree out of phase. So either if we want to have plus 90 degree out of phase, we will give the signal input at port 1. If you want minus 90 degree out of phase, we will give the input at port 4. Okay. This figure shows you a practical or physical realization of a branch line coupler. Why it is called a branch line coupler is simple. If you look at this, there are two parallel microstrip lines. One is at the top, one is at the bottom. Two parallel microstrip lines. These two parallel microstrip lines will be electromagnetically coupled to each other if we do not connect them physically. Now when there is electromagnetic coupling, in that case there is a small problem. Problem is because of coupling, sufficient power will not transfer from line 1 to line 2. because it is electromagnetically coupled. Electromagnetically coupled means mostly it is due to the magnetic field. Electric field plays a lesser role. So the power coupled from line 1 to line 2 is small. So when we require small amount of coupling, small power, when we are handling small power, then we can go for a non-branch line coupler, simple coupler without branch line. But when we connect these two lines using a branch, so from line 1 a branch comes to line 2, or more than one branch come to line 2, in that case we call it a branch line coupler, because a line or more than one line is connecting these two lines which are carrying the signal. Now look at this. Figure. In this figure, there are 4 ports, 4 junctions. Junction 1, junction 2, junction 3 and junction 4. The distance between junction 1 and 2 or junction 4 and 3 is equal to lambda g by 4. Lambda g is the guided wavelength. So within the guide, the wavelength within the guide, you know what is guided wavelength? Guided wavelength is free space wavelength divided by root over of epsilon effective, or root over of epsilon r. If you do not know what is epsilon effective, you can take root over of epsilon r, which is approximately equal to epsilon effective, very close to epsilon effective. So lambda g is equal to lambda 0 by root over of epsilon r. So this length is lambda g by 4. Similarly, the separation between the two lines, two parallel lines, is also lambda g by 4. Now suppose a signal comes to point 1, the junction 1. At junction 1 it will be divided. One will go, a part of the signal will go to junction 4. Other part will go to junction 2. From junction 2 it will get divided. One part will go to junction 3. Then from junction 3 it will again get divided and a part will go to junction 4. So the part that comes from junction 1 to junction 4 through junction 2 and 3 has travelled a length of 3 lambda g by 4. The part that has come from junction 1 to junction 4 directly has travelled a distance of lambda g by 4. Now lambda g by 4 is, in terms of phase, you know, phase difference is equal to 2 pi by lambda, or 2 pi by lambda g into path difference. If path difference is lambda g by 4, then 2 pi by lambda g into lambda g by 4, that is pi by 2. So pi by 2 path difference from point 1 to point 4. Similarly, 3 pi by 2 path difference from point 1 to point 4 when it comes through point 2 and point 3. So total path difference is 180 degree. Right, from 1 to 4, what is the phase difference? And the phase difference from 1 to 4, from directly from 1 to 4 and through 2 and 3, that phase difference is 180 degree. If there is 180 degree phase difference and amount of signal is equal, then they will cancel each other and nothing will come at port 4. Now how to ensure that amount of power will be equal at point 4, which means the power that comes directly from point 1 to point 4 and the power that comes from point 1 through point 2 and 3, they should be equal. How to ensure that? We have ensured that by changing or by designing the microstrip lines with appropriate characteristics impedance. So between point 1 and point 2 and between point 4 and point 3, the characteristics impedance will be Z0 by root 2. Similarly, between point 1 and point 4 and between point 2 and point 3, the characteristics impedance will be Z0. And if we choose such characteristics impedance, then the power which reaches point 4 from point 1 directly and the power that reaches point 4 from point 1 through point 2 and 3, those powers will be equal. If they are equal, they are out of phase, they will cancel at point 4. Other part is simple to understand. It goes from point 1 to point 2, so it will be in phase. Then it goes from point 2, it gets divided. It comes to point 3, so that will be for point 2 to point 3, there is 90 degree difference, so there will be 90 degree out of phase. So those will also be equal, they will be 90 degree out of phase. Why they will be equal? Because at point 2, we have two transmission lines at the junction. We have two transmission lines. Each is having characteristics impedance Z0. So same amount of power will go to point 2 and point 3. So that gives you the working of the branch line coupler. Similarly, this is a coupled line coupler in which there is no branching. The two lines, two parallel lines are there, but they are not connected. In this case, this is one which uses coupled lines like microstrip lines or strip lines will be placed close together. There is no direct connection between them. And if you want to know details about this, then you can go to the book, Pojar book. In the Pojar book, there is details about this. And the working principle is almost similar. The distance length is lambda g by 4, so you can say that port 1 to port 2 there will be 90 degree phase difference. Port 1 to port 4 there will be 180 degree phase difference. So between port 2 and port 4 there will be 90 degree phase difference. Port 1 and port 3 will be out of phase. So this has a 90 degree phase difference between the output ports, port 2 and port 3, and can also be used to obtain an equal power split or any other split ratio depending on the characteristics impedance of the lines. Now let us do an analysis of quadrature coupler. This analysis I will expect you to extend to rat race coupler. I will just give you hints about rat race coupler later, and you will extend the same analysis there. Here we are going to analyze the quadrature coupler. Port 1 will be excited. Similar analysis you can do by exciting port 4. Either of the two ports will excite. So port 1 is excited. If I excite the port 1, then there will be two types of analysis. One is even mode analysis, other is odd mode analysis. So to do even mode analysis and odd mode analysis, we require a plane of symmetry, POS. So here the plane of symmetry you can see through the green line. The green line gives you the plane of symmetry. So on the two sides of plane of symmetry, you can see the circuits or the diagram is the reflection of each other. So they are symmetric. Since they are symmetric, we can use odd even mode analysis because of symmetry. Now look at this circuit. In this circuit, between port 1 and port 4, the distance is lambda g by 4. So from port 1 to plane of symmetry, the distance is lambda g by 8. Similarly, port 4 to the plane of symmetry, distance is lambda g by 8. So that distance that you can use as a stub. This is, since we are using a POS and we are considering even mode analysis. In the even mode analysis, along the POS plane of symmetry, we have open circuit. So if you have open circuit, the transmission line which ends in open circuit is like a stop. So length of that stop is equal to lambda g by 8. So that part we now understand. At port 1, we are giving input voltage is V plus, it is coming towards port 1. So that is V plus is coming towards port 1. Exactly at port 1, the voltage, let us say at port 1 it is V1 even. Because it is at port 1, so it is V1. If we are doing even mode analysis, it is even. So it is V1 even. At port 2 it is V2 even. Similarly at port 3 V3 even. At port 4 V4 even. The lines which are connected to port 1 from left hand side and from the open circuit or plane of symmetry, their characteristic impedances are Z0. The line between port 1 and port 2 characteristic impedance is Z0 by root 2. Then at port 2, the lines going out of the port 2 and the line going out of the port 2 towards the POS, both have characteristic impedance Z0. Similarly at port 3 and port 4. Now what we can do is we can replace these stops, these open stops at port 1 and port 2 by equivalent admittance. How you are going to replace that by equivalent admittance? The input admittance of open circuited stop using transmission line theory is YS. YS is the admittance of the open circuited stop. So YS is equal to J Y0 tan beta S Ls. Ls is equal to lambda g by 8. Beta S is equal to 2 pi by lambda g. So put 2 pi by lambda g into lambda g by 8. That is pi by 4. So Ys is equal to J Y0 tan pi by 4. Tan pi by 4 is equal to 1. So Ys is equal to J Y0. So equivalent circuit of this excitation, port 1 excitation, will be like the one shown on the top right hand side. We have a transmission line of characteristic impedance Z0. Then there is a transmission line of characteristic impedance Z0 by root 2. At the junction, we are connecting an open circuited stop or a open circuit input impedance whose input impedance is J times Y0. Then at the second stop, at the second junction, similarly a stop is connected J Y0. Then after the second stop, there is this line whose characteristic impedance is Z0. So what we have three transmission lines. First one is Z0 characteristic impedance. Second one is Z0 by root 2 characteristic impedance. Third one is Z0 characteristic impedance. Two junctions of these three transmission lines, they are connected in series, so there are two junctions. At each junction, we are connecting an admittance with JY0. Now we will do after this. This indicates that we can use a simple ABCD matrix analysis to find out the net ABCD matrix of this circuit. That we will see later. And at the point 1, junction 1 and junction 2, the voltages are V1 even, V2 even. Input voltage is V plus. Now similarly for the second part, the lower part, you can see V3 even is equal to V2 even, V4 even is equal to V1 even. That is from symmetry, and we can find out the result. Once we find out the result for the first one, second one, the result will be repeated. Then the odd mode analysis. If we are going to do the odd mode analysis, how we are going to do the odd mode analysis? In the odd mode analysis, at port 1, voltage is V plus, input voltage is V plus, but because of odd mode at port 4 will give a voltage which is minus V plus. So if we do that, then V1 odd will be equal to minus V4 odd, or you can say V4 odd equal to minus V1 odd. Similarly, V3 odd will be equal to minus V2 odd. This difference will be there. Then at the plane of symmetry, in the odd mode problem, in the plane of symmetry, it is short circuit. Plane of symmetry represents short circuit. So since it is an odd mode problem, plane of symmetry will be short circuit. Under short circuit condition, input admittance of the short circuited stub will be Ys, which is equal to minus jy0 cot beta SLS. Beta SLS is equal to pi by 4, we know that. So Ys will be minus jy0 cot pi by 4, which is equal to minus jy0. And now, based on this, we will get the equivalent circuit. So equivalent circuit is shown in the upper right hand side. So you can take the equivalent circuit on the upper right hand side, that is the equivalent circuit. So we have two admittances minus jy0 separated by lambda g by 4 through a transmission line of characteristics impedance z0 by root 2 to the transmission line. There are two other transmission lines on each end of characteristics impedance z0. Input is V plus. At port 1 it is V1 odd. At port 2 it is V2 odd. We have to find out what is V1 odd, what is V2 odd. Then we can easily find out what is V3 odd and what is V4 odd. That we can do easily once we find this out. So now we are equipped to do the analysis for even mode and for the odd mode. So and now how we are going to do that? So consider the general case of the analysis. Ys, we have already seen Ys means the admittance of the stub will be plus or minus jy0. It will be plus jy0 for even mode. It is minus jy0 for odd mode. That we have just seen. For even mode and odd mode we have seen Ys is equal to plus or minus jy0. So instead of jy0 we can put Ys, and that is point number 1. Then, so that is one admittance, the admittances that we are using, that we know now. Then second part is we have three transmission lines. One is of characteristics impedance z0, other is of z0 by root 2, other is of again z0. So z0 by root 2 is connected on both the sides by z0. The ABCD matrix of a shunted stub is given as 1 0 y 1, where y is its admittance. So ABCD y is equal to 1 0 then y 1. So that we are now find out. Then the second part is we have a transmission line whose characteristics impedance is z0 by root 2 and the length of the transmission line is lambda g by 4. If we have a transmission line, its ABCD matrix for a transmission line is equal to cos beta L, jz0 sin beta L. Now in the first row, the second row is j by z0 sin beta L into j by z0 sin beta L, then cos beta L. So diagonal elements are cos beta L, off diagonal elements are j z0 sin beta L and 1 by j by z0 sin beta L. Now beta L is, since length is lambda g by 4, so beta L is equal to pi by 2. So put pi by 2 there. For beta L, put pi by 2. If we put pi by 2, then ABCD matrix of the line will be equal to cos beta L is 0. So put that 0. Diagonal elements will be 0. Sin beta L is equal to 1. So off diagonal elements will be JZ0 by root 2, JZ0 by J root 2 by Z0. Those will be the off diagonal elements. Why JZ0 by root 2? Because Z0 for the line is Z0 by root 2. Therefore, JZ0 by root 2. This will be, the lower one will be 1 by Z0. Z0 is Z0 by root 2. Z0 line is equal to Z0 by root 2. Therefore, that will be J root 2 by Z0. So that is for the quarter wave transmission line. That shows that the ABCD matrix for this circuit is ABCD matrix of the short circuited load or load line, shunted line or the Y line, then into ABCD matrix of the lambda G by 4 line into ABCD matrix of the shunt. There are two shunts. In between the two shunts there is a lambda G by 4. So ABCD matrix, as we have discussed already, ABCD matrix is, if you have series connections, ABCD matrix of the net connection is equal to product of ABCD matrix of each element. So use that. We can use that. Okay. Now, so ABCD will be 1 0 y1 into 0 j z0 by root 2 j root 2 by z0 0, then 1 0 y1. 1 0 y1 is for the shunted admittances and j0 z0 by root 2 j root 2 by z0 0, that is for the lambda G by 4. Now multiply the last two parts. So from the last two will come to the first one. So multiply the last two ones, that will give you j z0y by root 2, j z0 by root 2, j root 2 by z0 into 0. Then multiply that with the first one, that will give you j z0y by root 2, j z0 by root 2, j z0 y square by root 2 plus j root 2 by z0, then j z0 y z0y by root 2. Now we know y is equal to plus or minus jy0, plus for even and minus for odd. We are going to use that. So ABCD will find out for even, ABCD for odd, that will come.
You have reached Professor Mishra. Please wait while I connect you. Hi, you have reached Professor.
Yeah. Hello.
नमस्ते सर अजीत सर जो शास्त्री है ना पिलाने जिते से इतने शॉर्ट टाइम
बंद कर देवी क्लास को अच्छा
आगे
क्लास बंद कर देवी
हाँ सर से वन थे सारे ऑलरेडी आसल है हम वन थे ट्रे लिखी थी दो शॉप पे तो
कितने बजे लगे
आगे सर डिपार्टमेंट अपने जिते
हाँ ठीक है
आगे आगे
So since you have a program, we'll stop here today. Attendance measure. We have taken attendance. You can attend the lecture of Ajit.